Linda asked me, what is energy? And I had to think for a while. And I said, it's that which is necessary for change. So for instance, a rock is on the ground and you want to put it up on a cliff or up on a wall. Everything's the same, the rock is the same, but it's in a new position, it's in a higher energy state. So you had to provide energy to make that change. And I want you to look at the world through a lens of energy, which I've been doing now since I've been studying energy for the past 6-7 years. That the struggle to obtain energy for your activities is what has driven everything from the time in the beginning of life. The struggle to survive, to dominate. Whether it be the plants growing to obtain energy from the sun, shading other plants beneath them that they will perish, because these plants need the energy of the sun to build together their bodies to grow and reproduce. Whether it be that kind of struggle or the wars we wage in order to maintain access to energy sources that drive activities in our society that we find to be vital for us. We can look at the energy market. It's the largest commodity sold in the world, twice that of food. But again, we recognize this as a ridiculous statement because food itself is energy for our vital biological activities. So it's included in this. So the one thing we want to impress about energy, and you've probably heard this before, is that it's conserved. What does that mean? It means you can't create it, you can't destroy it. It's always the same amount, but it can change forms. So for instance, let's say we have a rock up on a cliff. We know that is a certain amount of energy, potential energy, the symbol is U, is equal to mgh, the mass times gravity times the height, where height is just, whichever distance you're measuring with respect to. Let's call this the ground. This is height is 0. So that's the potential energy this rock has. Now, if we give it a little nudge, it will fall off that cliff, and it will lose that potential energy. But that will be transitioned to kinetic energy as it falls. The kinetic energy equal to 1/2 mv squared. Now, when it hits, that kinetic energy is also gone, and that will change to heat. This energy is always the same. Inside a closed system, we won't lose any energy. But then you might ask yourself, how did that rock get up on the cliff? Right? Someone had to do work, which is equal to the change in energy, is equal to force, dot product of force times delta x. Okay, so this is Pete reaching in with his arm. Let's say the rock was originally on the ground. Pete reached in with his arm, did some work, providing that potential energy. And so that work was provided by an outside force. And so this work was put in there, and we could say the work of Pete is the change in energy he gave the system, is his potential energy. And yeah, it's equal to the force of gravity. mgh is equal to the force of gravity is what he had to push on the rock times the height he had to move that rock up. And so we can look at the rate at which he did the work is the power. Power is equal to how quickly you do the work over time, which is how fast the energy changes. You can look at it this way. So this work has a unit of joule, and you can recognize that would be a Newton meter for a joule. And how fast we do work, power, is going to be joules per second, how fast you can make the energy change, which is the same as a what? A watt. Okay, a watt is a joule per second, is the flow, the rate of flow of energy into a system. So if I'm a very powerful person, I could lift that rock up very quickly, run up the mountainside, let's say. And so I do the same amount of work in a very short period of time. However, if I'm a weak little person, if I'm a mouse, maybe I would need many pulleys, and I could do the same amount of work, but it would take a very long time, and I would have a very low power output. If we recognize then, energy is something that describes our state, or how much energy we can have. It's our stock. And power is the flow of energy, how fast it's flowing. And so let's take a look at where we get our energy from. Mostly we get it from the sun. Here is the earth, and the sun shines upon us. And the energy comes to us through radiant energy, okay, warming the earth. And so this is where most of the energy for our activities comes from, but also there's two others that are very small, and that is the earth is rotating. And so it has some kinetic energy. And we can actually harvest that in the forms of tides, because there's a certain bulge on this side and another bulge on this side, especially if the moon's over here, right? Your tides from the moon are bigger from the sun. And we can harvest the energy as we rotate through these bulges. And there's one other source of energy, and that is nuclear. So we have this, like uranium, for instance, inside of the earth. And we can use it in two different ways. One is we mine it and we use it in reactors. But also, that's what makes the earth hot on the inside. And that geothermal energy is actually a form of nuclear energy, because the earth wouldn't remain hot if it weren't being heated from the inside. Okay, so we recognize all of this energy is coming into the earth from the sun, mostly from the sun. And its energy must be changing if the energy was constantly coming in, but the energy is actually also going out at the same rate. And that is, the earth is radiating infrared radiation out into space to keep a balance. So all of the energy that comes in from the sun is eventually radiated back out into space, and at the same rate, so that the change in temperature of the earth stays constant. Now we recognize that's not perfectly true with this climate change thing, that we're putting a little bit of a coat around the earth with the carbon dioxide, and so therefore we've reduced this infrared radiation because it absorbs it, kind of like putting a down coat on the earth. And so what's happening is the temperature of the earth is, yes, going up just a little bit, because slightly more energy is coming in from the sun than going out. And when the temperature goes up, we'll radiate more, bringing us back into equilibrium, but at a higher temperature. This describes all the energy flows in the earth, or to the earth. An energy flow is an arrow. Okay, so we show these arrows, and an energy stock is a circle, okay, where we store energy on the earth. All of the power use, the rate of energy use of the human race is 15 terawatts, or 15 trillion watts, right? But this is a little bit old, so now it's probably about 18 terawatts. And you ask yourself, do we have that much energy coming in from the sun? And we recognize huge amounts. Okay, we have 162,000 terawatts. So the ability of us to obtain our energy, theoretically, from the sun should be very easy. There are two other sources of energy, and one is nuclear. Okay, part of it is the nuclear energy that we have inside the earth, such as uranium that we can use. But also, it's this decay of radioactive material inside the earth that provides the thermal energy to drive geothermal processes. Okay? And the last source of energy is the kinetic energy, because the earth is turning. And how can we harvest that? Well, we have these tides that stick out on either side from the sun and the moon of the earth, and we can harvest that energy. And you can see we harvest a tiny, tiny amount of energy from tides. In fact, these tidal energies are very small, 3.7 terawatts, the rate at which this power is dissipated, compared to the 162,000 terawatts from the sun. And the geothermal energy, again, is very small. And we can see that our nuclear fuel provides us with 1 terawatt. Okay, so on the order of 1/18th of all the energy that we consume as humans. But we recognize it'd be reasonable to say that the sun provides us with essentially all of our energy needs, whether it be directly heating the surface, or through photosynthesis. 90 terawatts is converted to plant matter. And so here, this is all of the energy that's presently exists as plants. But old plants constitute coal, right? Deep in the earth, lots of energy, oil, and natural gas. And this is the rate at which we use that energy. So this is our power, or our rate of energy use. 3.6 terawatts are being dissipated on average all the time from coal, 5 from oil, and 3.2 from natural gas. And so we can expand our energy flow that we just talked about with Pete picking up the rock. What did we have? Well, the rock had potential energy, right? And it turned to kinetic energy through the virtue of the force of gravity, right? Also, the rock was lifted up from the ground by virtue of the work of Pete. But where did that energy come from? Oh, that came from Pete's huge muscles, which the energy actually, so the power came from the muscles, but they were just converting, this energy, this chemical potential energy in Pete's body, this ATP, into the potential energy of picking up the rock. Well, where did the potential energy from the ATP come from? Well, that was from the chemical potential energy in Pete's food, the glucose. The food turned to glucose, turned to ATP. So where did that food get its energy? It could have been beef, right, who ate plants, but ultimately it came from plants, and that came from the radiant energy of the sun. Now you could say, yes, the sun has nuclear energy through fusion, but it's enough for us to say we're getting radiant energy from the sun. And it turns to plants, which I eat, make that ATP molecules, which drive my molecular motors, and that work gave potential energy to the rock as I picked it up. The force of gravity pulled it down and gave it kinetic energy. It hit the ground. This kinetic energy turned to heat, which we symbolize as Q, through the force of friction as it hit the ground. And that Q ultimately radiates out into space, into heat in the space. So this would be like radiant energy, IR, into space. So it comes from space, from the sun, it radiates back into space. Now, I don't mean to say all of the energy from the sun goes to the food, goes to the ATP, lifts this thing up. We recognize along the way a lot of the sun's heat does not go to food. It just goes to heat up the earth, and that radiates out. As well, not all of my food went into ATP. Not all of the ATP went into work. So these processes are not 100% efficient. A lot of energy, is we could say lost to heat, which ultimately radiates out. But we can define the energy processes that are central to this rock as radiant energy turning into chemical potential energy, the work providing potential energy, gravitational potential energy on the cliff, to kinetic energy, to heat, and then radiated back into space.